Okay. Somebody sneezing in the background. Okay. All right. So, optical fiber test, part 2. And today we're going to take care of practical application. All right. Cool. Test 2. All right. Test 2 is going to be deployed next week. It's going to be on the same basis as it was. I just wanted to get you to the point that I'm going to give you this presentation right now. All right. So, and it is going to be since the test 1. So some parts from quiz 2 could be on the same on that test. All right. Okay. So optical fiber practical applications today. What we can see on the first screen right now is what does it remind you of? All right. Anything familiar that what we have done in the last couple weeks with the copper side of our side of the world here, or our telecommunications planet? No takers. All right. So I'll tell you, this would probably remind you of something that would be a patch panel. All right. The only difference between this and the patch panels that we talked about in the past few weeks is that this is a patch panel that will accommodate optical fiber connections instead of the copper connections. All right. So here is the fiber tray. So it's a fiber patch panel, fiber connections. As you can tell, there is a single rack space unit, and there's just 17 inches across, and that's like, I think it's 2.5 inches tall, so that would be single rack space. The patch panel that we used to practice on was just a single wall-mounted patch panel. But in the demonstration video, I also showed you the rack-mounted patch panels as well. So in order to organize the fiber optic connections, because when we do the telecommunications connections and connecting all kinds of signals that have to be routed here and there and everywhere, some sort of organized way is called for, because if you would just connect a bunch of things and throw them in the some sort of a drawer or a space, it would be impossible to service, impossible to make out what is what. All right. So these would be the couplers, right? Optical fiber couplers, which you would have optical fiber connector with the fiber optic connected to it. You would plug it in from this side, and another cable, optical fiber, would be plugged in from the other side. They would be aligned carefully, and that's how the light signals would pass through this type of a connection here. Okay. All right. So today we will cover cable types such as loose tube, tight buffered, and ribbon, which ribbon kind of goes together with the loose tube. And the big difference between these two, loose tube and a ribbon is basically a loose tube, but it's arranged in a slightly different way. The tight buffer is has a significant difference. There's a significant difference between these two, loose tube and tight buffered, and we will cover that knowledge right now. All right, so you could probably follow the post-it notes. You could see things more clear on those notes, but I'm just going to describe what we see here. This is the part of loose tube cable, right? So that's the first one that we're going to. Loose tube, all right. Now, it consists of PBT material filled with thixotropic jelly compound, PBT, polybutylene terephthalate. I hope I pronounced that right. I'm not going to test you on the pronunciation and the characteristics, or the chemistry that has to do with it. But we'll cover some aspects of what those actually are. All right. So number one is right here. That's the strength member right here. No, sorry, that's not number one. These are the tubes. Sorry, scratch that. These are the tubes right here. So we could see a big cable with some protective layers here, and there would be tubing, right? And in that tubing, there would be fiber strands, and they would be arranged loosely. And we'll cover the reason why those are arranged in such way, right? So PBT filled with thixotropic jelly compound. Well, why PBT? The PBT, well, here, right? Kind of polyethylene, or here's the difference between the PE and PVC, right? Because sometimes, I don't know, here. First, we're going to talk about the thixotropic. What's a thixotropic? Thixotropic fluid is one that takes a fixed time to return to the equilibrium, which is the balance of viscosity, which is another way thickness, when subjected to abrupt changes in shear rate. In other words, the liquid becomes less viscous or thinner, becomes thinner or flows more easily when shaken, stirred, agitated, and otherwise stressed. The fluid then, after that, recovers to the original viscosity. The reason for that is that those tubes are sometimes filled, or most of the time would be filled with that thixotropic jelly compound, and that has to do with the protection, physical protection of that. So when the temperature goes up and down, the thixotropic jelly behaves certain way in order to protect the optical fibers, because the optical fibers are glass. We also have plastic optical fiber right now, but for the most part it will be glass, so that has to be protected. Okay, now number two right now here is we could see the optical fibers. That's the main reason why everything else is built around it, right? So the optical fibers is the most important thing. Basically, that's what carries the signal, right? Now then we have a central strength member, FRP, or non-metallic. FRP, fiberglass reinforced plastic. All right. The purpose of that is basically to provide additional strength for the whole cable. Right? If necessary, central strength member right here, central strength, might be coated by black PE. And what's black PE? PE, polyethylene. Polyethylene is the next generation of plastics that comes after the PVC, right? And you can see the differences. Basically, it's more durable, protects things a little bit better, and it's more modelable. Okay? So, in other words, nothing but the best is supposed to be applied here in order to give the best protection for the thin optical fibers that are inside those tubes. I'm losing my mouse here. Right? Then core filling. Where is it? Here, core. Dry core water blocking yarn or thixotropic jelly as well. That's in there. Again, moisture gets in there, hot and cold temperatures, because these these cables, these optical fiber cables, are mostly installed outside, between the utility poles. So they are subjected to temperature changes, hot in the summer, cold in the winter, and whatnot. The wind is blowing, moving them around, so things have to be protected. Now there's a core wrapping tape, just water swallowable tape or polyester tape. That's the white stuff right here. It's one of those things that did you ever have? Did you ever see the something like a survival kits or something? It was like a napkin in a pill. So it will be just like a little tiny pill. You drop it in the water, this thing expands because it's soaking up the water and it becomes a huge kind of a napkin that you can use. All right, so that's basically this thing can take a lot of water. So wherever you have things outside, you just can't escape the fact that moisture in the air constantly trying to get in there, and some of it is actually going to get to that thing. Moisture protection is also a big thing. Now, if you add moisture and cold temperatures in the winter, things could get a little bit edgy. So that's why those things are protected. And then there's an outer member as an option. There could be also sometimes you're going to see something that's called an agent, which would be a steel cable incorporated into the whole cable in order to hang things overhead. Right? So that's also providing some protection as far as the distributing the forces due to the gravity. Right? And that usually it comes with a lot of telephone cables as well, which is the copper wires. So the wire is not just basically supported by itself only. So it could be subjected to all kinds of stretching and stuff that has to do with the gravity pull down. All right. So the hit is being taken by something that's called the agent, which would be the steel wire going between those utility poles, and that's what is providing the physical support, and the rest of it is basically tapped into it, or not tapped into it, mounted onto it. Right? And then there's that outer jacket, right here. Right? You see those cables all over the place, and in the next few slides you're going to see where you can see them, and next time you're going to be driving around or walking around the street, you are going to see them everywhere, these optical fibers. So just wait for this next couple of slides here. All right, so here we have a little bit of that. Now, loose tube cable. All right, the loose tube cable is designed for harsh environments. Right? Now, first of all, why is it loose? What is it called loose tube? Basically, because this whole cable consists of multiple number of tubes. Like, see, there's a violet one, here's the yellow one, the green one, and in those tubes, those optical fibers are inserted loosely. They're just there. They could wiggle around. They have some wiggle room. Right? Why is it loosely inserted loosely? Well, one of the main factors is the expansion and contraction of the material due to the temperature changes. And of course, most of the materials tends to shrink when subjected to cold temperatures and tend to expand a little bit when subjected to the other side of the spectrum of the temperature thing, which would be hot temperatures. All right. So if you pack those optical fibers tightly in those tubes, if let's say a nice cold winter day or night, those tubes would contract and they could actually squeeze and damage those optical fibers. So that's why it's called a loose tube cable. All right? So it's designed for harsh environmental conditions in the outdoors. Fiber strands floating loosely in the designated rugged tubes, as just like we see it on the picture here. Materials contraction and expansion due to temperature changes will not affect the fiber strands, used mostly in the outdoor long-haul installations up to 120 kilometers. Right, so that's the loose tube. Where can you see that loose tube? Did you ever walk down the street and see between those utility poles that barrel-looking object, those barrel-looking objects like this? Yeah. Well, those objects are called a FOSC. FOSC stands for fiber optic splice closure. And when you take that cover off, and we do have one in the lab, I actually put that on the AV card so you could just walk by and see it. Excuse me. Inside those FOSCs, we have optical fiber cables coming in, and they are sealed to protect from the moisture and dust and whatnot. And on the other side, they're fanned out, and those optical fibers are being arranged in a way that they are needed. So there could be one cable coming in to that FOSC that goes to one side of the world. It goes towards, I don't know, maybe Dorchester or Ingersoll or Woodstock from London. And the other cable goes the other way towards maybe Sarnia, right, or towards the rest of the city. And they have to be spliced. And usually, well, pretty much all the time, there is this type of splice is being used on that is a fusion splice. The one that we are actually practicing in our last lab. This is the last part of our course. So we are performing the fusion splices during those labs. So basically that's what is taking place when servicing those FOSCs. Not only that, inside those FOSCs, sometimes there's some other equipment that's associated with that. There could be splitters and whatnot. Or attenuators. So depending on what the company that does, depending on what, but usually it's just basically a splicing happening there, right? So there are a bunch of trays inside, and inside those trays there would be fiber strands just going around, and the other one from the other cable going around there, and they will be put in a protection sleeve and fusion spliced and inserted in that bracket, those brackets right there. All right, so that's basically what's taking place in those FOSCs. There's a bunch of videos you can see on YouTube of multiple people showing how to service the FOSCs. I'll just give you one example here of what's happening as far as the cable preparation for the FOSC. There is no fusion splicing going on this video, but if you just keep following the trend of that, then you're going to see a bunch of other videos that have to do with the FOSC service, installation, fusion splicing, and whatnot. Right. So I encourage you to just take a look at that. But I might ask you on a test what FOSC means. Right. So basically, the idea of the FOSC is sometimes you would see the utility pole right here with the overhead wires. Can we see that? Yes, we can. And this would be maybe the power lines, and sometimes not. All right. And a little bit lower, you're going to see the communication part of it, right, going there. So this would be the telecommunications. There could be telephone wires. There could be, for the most part, there will be optical fibers. And you're going to see those FOSC somewhere here, like a barrel-looking object. And over there, you're going to see a slack of the optical fiber. Right? The purpose of that slack is so you could take that FOSC off the main line here and put that inside well, there will be usually somebody services that you're going to see a ladder here happening. This is the ground, all right? And then you're going to see a van. Let's see if I can draw a van. Here are the wheels, all right? And at the back of the van, there will be an opening here. And you're not going to see that because it will be taken off. And this FOSC would be taken with that slack inside that van. So you have a nice, clean and dry environment. And inside, there will be a working bench, and the technician would basically open that FOSC, service that, do some additional splices, maybe insert some more wires, whatever needs to be done, and then they would just go take it out after sealing it back, putting it together, and hang it right onto that overhead wiring. And so sometimes you're going to see that. So that's what's happening. Okay. All right. All right, now from the loose tube, we're going to move on to the tight buffered cable. Right? May I point to you that this looks like an orange type of a cable, so which suggests the orange jacketing suggests that it is a multi-mode fiber. Yellow would be, for the most part, mostly yellow or orange. Yellow would be single mode, orange would be multi-mode. Now we can see a little bit different structure of that. It's a tight buffered. Instead of loose tube, those fibers are packed tightly with some soft material, and it's the Kevlar. Right? It's a Kevlar. Kevlar is silky type of strands put together. Also, Kevlar is the material that the bulletproof vests are made of. Right, so that's supposed to serve as a protection against physical bumps and whatnot. All right, so here's the outer jacket. All right, here's the armored yarn or Kevlar. Then there would be a ripcord, just like we used the ripcords in the copper cabling. And then we have the 900 micrometers tight buffer optical fiber strands, right? And inside those, you have the 250 micrometers or microns optical fiber. And then, as we remember, what's the size of the cladding inside? 125 microns. And you would have something like 50 microns, the core. All right. So the purpose of where these guys are being used is mostly in the LAN configuration. You could not use this outside because this is tightly packed for protection. And we could afford to do that because we are installing that in the LAN environment inside a room that the temperature is being pretty much controlled. The temperatures don't get to extremes either way, right? So that doesn't come to play as far as extraction and compression of the materials. So then we are able to install that inside a LAN configuration. So the loose tube uses single mode single mode fibers, and they are for long haul applications up to 120 kilometers. Right? Remember the copper wires, Ethernet, we're only able to have a link that is 300 feet long. Now 120 kilometers, that's a lot longer than 300 feet. Right? Now when it comes to the tight buffer, this would be the LAN configuration within the LAN environment, connecting equipment together whenever you need distance longer than 300 feet and bandwidth that is a lot bigger, and we're going to compare that than the copper can provide. Right? Safe distance to run these cables would be 2.5. Sometimes some sources are going to give you up to 3 kilometers. So that's a lot, when you need to connect the telecommunications closets, all right? So the copper cables would be from the closet towards the end user, computers, wireless access point, telephones, whatnot. It will be the copper, Cat5e minimum these days. This is 2021 right now. There will be another closet somewhere else if it's a big building that will accommodate the distance for the equipment, and there will be another closet somewhere else, and those closets, IDFs, intermediate distribution frames, they would be connected with the optical fiber to the main distribution frame, MDF. Right? So that's how things are usually solved these days. In some companies decide to, instead of using they just skip the copper all around. Then they would also have optical fiber going to the desktop, depending on the setup. It is possible to have fiber going to the desktop, but in order to cut the costs, and that is still going strong, the copper is being used. So Ethernet type of cabling. Right? So here is a loose tube. What does it look like here? Okay, well, it's just a summary of the loose tube. Designed for indoor application, fiber strands packed tightly within the armid yarn and wrapped with the outer jacket. Right? More flexible than the loose tube. Well, the um, the optical fiber. This is my phone charging cable, but you have the consistency like that. All right, this would be the loose tube. Tight buffered. Okay, for the LAN applications. When it comes to loose tube, it would be almost as hard to bend as this pen that I have. Of course, if it was longer, you could bend it somewhat. More flexible than loose tube cable, but also more fragile. Used mostly indoors in LAN environment. And this would be an example of how the tight buffered cable is being used. Now, tight buffered cable can come in multi-mode or single mode configuration. This is an example I took it from the internet. It looks like this is the single mode cables with connectors installed, and they're put into those couplers or into the inputs of equipment that utilizes the optical fiber link. What could this possibly be? All right, what can we see here? We do see something like transmit and receive link for the optical fiber within the LAN configuration. And what do we see here on the top? That looks like an Ethernet connection. So here's a copper and here's the fiber. So probably this one module would serve as something that we talked about, would be a media converter, which would convert this type of signal, electrical type pulses signal, in electric form into the light pulses. So there you go, a media converter. Here's a stack of them. Right? That's what it is. All right, now we talked about the loose tube, we talked about the tight buffer, and now we're going to talk about something that's called a ribbon cable. Now, why did I say that ribbon cable and the loose tube, they're quite similar to each other. It just has to do with the specific type of arrangement that is used in order to insert those fiber optic strands into the tubing that's there. If you just throw them in loosely, you can only put them so much. But if you arrange them in straight ribbons, just like those ribbon cables that you use inside the computers, but they're optical fibers, then you can actually save some space if you put them in some sort of organized way, and you can have more of them in that tube than you would if you just pack them loosely, right? Also, what the advantage of that would be that there's some splicers or fusion splicers that instead of connecting, it takes some time to fusion splice one single mode cable, for example, or cable, the strand, right? Because cable would contain multiple strands, right? So one strand, it takes about a certain amount of time, depending on what equipment that you use, newer, older, or more expensive and less expensive, right? Excuse me. If you arrange them in ribbons configuration, there are fusion splicers that you can put a whole ribbon on maybe 6 or 12 strands in one end. They can put another ribbon in the other end, and with one sort of action, the whole ribbon is getting spliced instead of all those one by one, right? So let's just take a look at the summary here, and the other part of the other aspects of the construction pretty much remain the same. They can see here there's a little bit more of the strength members right here, right? And the protection depending on who makes it and where it is supposed to be used, but usually this outer jacketing here for the whole cable is pretty much quite tough. You can't just use your X-Acto knife and strip that cable. It's a chore to strip that one, right? Plus, you're supposed to strip the whole tough elements of that without damaging the cable as well, the fiber strands. All right, so the summary of that: ribbon fiber optics, the ribbon cable. Ribbon fiber optic cable is arranged into a strip. It's a convenient solution for space and weight problems. Well, if you have how does it solve the weight problem? Well, if you need so many optical strands from one place to another, and if you have just loose tube, then you can only pack so many of them in loose tube configuration, and then you're going to have all the other paraphernalia that goes around it to produce the cable. So yes, I would consider the weight as well, and the whole thing has to be suspended overhead, for example, in between the utility poles, right? So it's a convenient solution for space and weight problems. The cable ribbons are actually coated with optical fibers placed side by side, encapsulated in mylar tape. So yeah, basically that's how they are constructed. Similar to the miniature version of the wire ribbons used in computer wiring, a single ribbon might contain 4 or 8 or 12 optical fibers. And you can stack those ribbons up to 22 ribbons high. So then we're talking about some efficiency as far as the number of optical fiber strands that we can pull from one side to another. Right? Now, let's take care of the color code that has to do with those optical fibers. Remember blue, orange, green, brown, slate? Blue, orange, green, brown, slate. So first 5, it's just as the 25 pair cable color code for the copper cable. But we are dealing with some more, because we're not dealing with pairs right now. We're just dealing with individual strains when it comes to optical fibers. So the color code had to be rearranged in a slightly different way. But what do we have? Blue, orange, green, brown, slate. Slate stands for gray. So number 6. So this is 24 optical strands. Blue, orange, green, brown, slate. Then goes white, red, black, yellow, violet. Violet, sometimes indigo, rose, and aqua. Right? I'm a man, so women tend to see more colors than men can. But after a while, we can pretty much stand up to the task as well. All right. So then that's the first 12 strands. All right. Then the 13 to 24, you have those blue, orange, green, brown, slate, but with black stripe, except for the white one. Right? Sorry, no, the white also has a black stripe, except for the black, because you can't have a black stripe on a black conductor, if you can call it that way, or wire. Then it's just reversed. So there's and everything else has the same colors with the black stripe. Right? So that's the color coding as far as distinguishing the. You see here. There you go. Now you can see the color coding on those ribbons. Right? All right, the color code for the jacketing. So we were talking about the optical fiber strands, but now we're going to take a look at the jacketing, which is basically the whole cable jacketing. Right? Now we could see multi-mode. And then over here, we could see single mode. Right? Different cables, optical fibers, came out into production as the years went by and as the technology was improving as the time passes. All right, so that's why you have certain amount of cables that we're dealing with. All right, so just a regular multi-mode. And over here we have the non-military, which is most of the time we're going to be dealing with, and also there's a military color code. Right? So multi-mode, let's just forget the military code. Just concentrate on the regular commercial type, right? And if you want, you can just also reference yourself towards the military stuff. And if you have to work with that, you're going to be trained and you're going to deal with that. So you will acquire that information. But I just want you to see that something like that exists as well. All right. So just a regular multi-mode. All right. And here is the core, and here's the cladding size. For the most part, you are going to see that the cladding all across the board here is 125 microns, except for the old original multi-mode, it would be 140 microns, and the core would be 100 microns. So that would be the older one of the first ones that were produced. And jacketing would be orange. Then OM1, OM2, OM3, OM4 that we have, so optical multi-mode designation 1. Then time goes by, the technology improved, they came up with some better cable. So they call it different generations, right? So as time goes by, the cables, the optical fiber becomes a little bit better as it's produced, right? And it had to be called something. So the optical multi-mode, right? Here, optical single mode, right? So you can see OM1 is 62.5 micrometers, the core, and the cladding, of course, is going to be the 125 microns all across the board. This will be also the older one, OM1. Now, when it comes to OM2, OM3, and OM4, you can see that the core is 50 microns, and that's if you're like these days, right now, if you're going to do some optical fiber installations right now, you're going to most likely, or pretty much for sure, you're going to use the 50 microns, and the cable is being stocked, so you can pretty much walk into distributors and they'll have it on shelves. If there's some older installations, and may I say that the optical fiber does not deteriorate as quick as the copper cabling, which oxidizes and has to be replaced once in a while. The optical fiber can last years, so you're still going to see some of the 62.5 microns equipment utilized. So it might take you about a week to order that, but they're available as well. Right. The OM1 orange multi-mode, OM2 orange, and then OM3 and OM4 you're going to see aqua color jacketing, and then you see the single mode are pretty much yellow jacketing. Right? If you see yellow, that means a single mode. If you see orange, it's going to be a multi-mode. If you see aqua, it's going to be either OM3 or OM4. You just have to read it further. And it's just, they have different specifications. We're going to take a look at them. Remember this chart right here? This is Cat 5 right up to Cat 8, sort of. So Cat 5 obsolete. What can we see here? Distance, maximum length, 300 feet. All right, Cat 5e, maximum length, 300 feet. Cat 6, maximum, pretty much everything is up to 300 feet, except for that Cat 7, that if you want to get that 100 gigabytes, you can only get this thing up to 50 feet end-to-end length. Excuse me. So now let's and the transfer speed versus bandwidth. Okay, just as a reminder, transfer speed is the digital signal that's being transferred over the link, and the bandwidth is the radio frequency that you can inject into a cable that the cable is capable of carrying and actually have that signal on the other end, and that could be actually understood by something that's receiving it, right? So the bandwidth might be a little bit different than the transfer speed, because the transfer speed just uses tiny little pulses. You can compact them a little bit more than the frequency of the analog signal. And also, as a reminder, the internet that is provided from the street to your house is in the analog form, so the bandwidth comes in play. And when it comes to the speed of your network, computer network at home or in a business, commercially, then it's the Ethernet, it's the digital form of the signal, and the speed transfer, also the transfer speed comes in play. And you can see that most of the time, the speed transfer is going to be faster than the bandwidth. Right? So that's the slide that we had last time as far as the copper cabling. Now let's compare that to the optical fiber. Right? Now look at this. We have lengths here. Over here on the x-axis, we have the length, and it's not in feet this time, it's meters. So here's 2,000 meters, so it's like 2 kilometers. And it continues more. This blue area here, it's not nothingness. It's basically, look, OS1 and OS2, which stands for optical single mode and optical single mode. Right? So let's take a look at this here. OMs. OM1, all right, 62.5 microns core over 125 OM1. It can deliver 100 megabits of transfer speed up to 2,000 meters, which is pretty good still, right? Then OM2 can give that 50 microns over 1,500 meters only, all right? So we can give, now, what can we have here? 1 gigabit per second, only up to 300 feet, meters, right? And let's say OM3, OM3 can give us 1 gigabit transfer speed up to 800 meters, so it's almost a kilometer, right? Now OM4, which is the later generation, it can give us 200 meters more, up to 1 kilometer. It's a multi-mode signal cable, all right, optical fiber. Then 10 gigabits, OM3 can give us up to 300 meters. OM4 can give us up to 500 meters, so the transfer speed, you can put more data over time. 100 gigabits per second, over 100 meters, we can get out of the OM3, right? So that's how you read this thing here. Now, if you look at the blue stuff here, this thing just continues. And remember, we talk about up to 120 kilometers. Well, usually when it comes to running a single mode signal, depending on who makes the equipment, what type of fiber is installed, and when the information was printed, you're going to see information like maybe 50 kilometers, 100 kilometers, or so on, without the need of reinforcing the signal anywhere along the way, right? So that's the difference between the signal speeds and the distances that the signal can be carried between the optical fiber and the copper. Of course, copper is much less expensive as far as production and installation and the equipment that goes around it than the optical fiber. So money talks. All right, so as a summary of this part here, single mode cable is a single strand of glass fiber with relatively narrow diameter, about 8 to 10 microns, so that's a single mode. And according to some sources, 5 to 10 microns. Typically, it's 9 microns. All right. Usually, it has one mode of transmission, which is basically one beam of light. If you can translate that into that, what a mode is, that doesn't bounce off the edges. Yes, it kind of travels in a wavy way a little bit, but it's microscopic. That propagates at the wavelength of 1310 nanometers or 1550 nanometers. On that account, there will be a little light reflection when the light passes through the single mode fiber core, meaning ideally the light will travel in an ideal straight line in single mode core. In reality, the light travels in a subtle wave grazing against the interface with the cladding. Right? Consequently, it will reduce the fiber attenuation, optimize the speed for the transmitting signals. Right? What does that mean? It means the transmission distance is the significant performance advantage of a single versus multimode fiber. Single mode fiber is usually used for long distance signal transmissions. Okay? Now we'll talk about the connectors, and then we'll talk about the water bands. Right? Connectors, well, in order to, the best way to join two optical fibers is through a fusion splice, which we are performing during this lab period that we're doing now. However, using connectors to transfer that the signal is also a possibility and quite efficient, may I say. So there are two types of connectors I'm going to show. The SC connector stands for Standard Subscriber Connector, and the LC. Right? The difference between these two, that the SC, the standard, and the Lucent connector, the SC are a little bit bulkier and bigger. It's about 5 millimeters square type of thing. Now these are significantly smaller connectors, which gives us an advantage pretty much of how many of those connectors we can put into single, that kind of a patch panel that we're talking about, right? So that these are the mechanical, non-mechanical. These are the connectors that are being put onto the optical fiber. I'm going to include another video that we did a couple of years ago with Mr. Cunningham that involves installing a mechanical splice or connecting an optical fiber onto a connector using a mechanical splicer, which means the fusion doesn't take place. The temperatures do not fuse weld glass into the whatever else it is. It's basically a mechanical alignment, careful mechanical alignment. So the core is basically aligned with whatever the ferrule of that jack or the connector. And then there's some index matching gel, which is supposed to, if you have that little gel there, so called index matching gel, then the light is going to pass more smoothly through that actual interface that is basically based on touch. All right. So I'm going to include that video because sometimes you're going to have to perform the mechanical splice, and when you watch that video, you will know how to. All right. Quite often right now, those optical fiber, the jacks, the connectors, you can buy them in prefabricated version that you're going to have a little tiny piece of fiber sticking as a tail from that. So the optical fiber is actually already mounted onto the connector by the manufacturer, and you have that tail end of that, and you use a fusion splicer in order to connect the that connector with the tail end of it. So they call the pigtail kind of configuration. You can just basically connect that using a fusion splicer, which is becoming more and more popular right now. All right, this is the Alder connector, straight tip connector. If you see something like that, this is also of optical fiber. You're going to see less and less and less of these connectors. All right. Typical wavelengths. Before we go, I really want to give this thing to you, okay? Because this is important. All right. So bear with me for 5 more minutes. Let's see how many people are left. 8 people are left. I guess everybody else is going to watch it on YouTube. That's fine. All right. Typical wavelengths. While it is common to use frequencies in hertz, we just talked about that last time, to specify the transmission bands in radio communications, optical fiber communications is set to use wavelengths in nanometers. It's just how things have settled. All right. Now, typical wavelengths. Remember, we had the 850, 1300, and around 1550 nanometers wavelengths. And here's the attenuation. And here is the attenuation. So see, these are the longer wavelengths, which means the frequencies are less. So we are entering the red or infrared region here, and we're getting more red to the point that we can't see it anymore, but the energy is still there. It's called light. Okay? So the attenuation is greater as the frequencies are higher, and the attenuation is lower as we lower the frequencies, which is lengthening the wavelengths. Right? Optical communications relies on the transmitting the signal in the form of light through the translucent medium, glass or plastic. Ideally, the scenario would be as following: shine the light through the glass rod and receive it on the other end. In reality, the efficiency of the transmission is related to the wavelength of the light. All right, for the transmission to be most efficient, it needs to bear the least amount of obstacles, such as attenuation. Well, it passes through a physical medium, so it is going to weaken the signal, right? Scattering and absorption. This is something, well, attenuation exists in copper as well, right? But we don't see the scattering and the absorption in copper as much, pretty much almost none of it. But when it comes to light, these two quantities right here apply more to the light. What does it mean here? When it comes to attenuation, so we know that already, what that means. Scattering, all right? Scattering. Certain wavelengths interact with the silica molecules of the silica glass, right? This interaction results in light being scattered along the transmission pipe, I put in quotes, and becoming unreadable as the signal. Here's the bottom image, all right? So there will be silica molecules, and the light passes. It could actually bounce off those molecules and just scatter all over the place, making the signal unreadable. It happens to certain frequencies. Absorption, right? Certain frequencies, when interacting with the glass medium, well, here's the thing. The glass, you can't make a perfect glass, although we have accomplished that somewhat by now. But the idea is that no matter how much you try, you are going to have some sort of moisture, as little as it may be. You're going to have a little bit of a moisture trapped in that glass as you're making the glass. And then you're stretching it into the fibers, right? Those water molecules, sometimes they have the power to absorb the light under certain frequencies. So when there's certain frequencies, there's no interaction between the water molecules. And certain frequencies or wavelengths, when it comes to light, that those water molecules are going to interact in a way that they're going to absorb the light. So you just won't see it at the other end. So that's why when it comes to absorption here, so here is the most of the time we're going to see the scattering. Now, absorption happens here between the between those spikes right here. So the 1300 and 1550, that area is good for transmission because the absorption and the scattering doesn't happen. Right? So that's why, remember when I told you that I'm going to tell you why we have those certain frequencies. That's why, right? Now, there's some newer optical fibers that are called the full spectrum or zero water peak fibers that you can transmit pretty much most of the frequencies because the technology has gone so far that there's almost non-exist. The water particles almost do not exist in there, but for the most part, you still are going to see the optical fibers. And these three frequencies, pretty much around these, are the good for optical fiber transmission. So that's why we have those frequencies and not others. All right. Now you can see the optical fiber primary transmission lengths for the optical fiber 850, 1310, or 1550 nanometers. All right. And here is the plastic, multi-mode, and single mode most common wavelengths. All right, 650 nanometers for plastic and 850 nanometers are the most common. Multimode or graded index. Now, here's the thing that I didn't talk about. Here's your homework. Find out what graded index is. right? Then 850 and 1300, around that, for the multi-mode organic index. Then single mode 1310, and here's the other frequencies. That'll be typical frequency 1550 with the typical frequency for signal transmission. Okay, so here is the last slide. Okay. And we're probably going to see each other one more time with some sort of review of what we have done. I'm going to deploy the last test, this next coming week. Of course, it's going to be on the same basis, so there's no set date. You know how it is. Just we have done it as all the other tests and quizzes. Okay, cool, guys. You're ready to go to the next class. Some of you already did. And I will see you when I see you next time. All right, thank you.